In this lesson, I will briefly introduce principal component analysis in R and how to extract information, along with a couple matrix operations which are of importance to this algorithm. This lesson touches on some more advanced mathematical techniques, but I wanted to cover it briefly because it's a very powerful tool for expressing the variance within a dataset, and you may find them very helpful. First, let's load the iris dataset and attach it. So there are two functions to extract the principal components of a dataset. There's prcomp and princomp. Both use a different method to reach the results. prcomp uses a method called single value decomposition of the data matrix. The first argument for this function was the numerical variables of the iris dataset. The second argument, scale, tells the function whether it should scale the information before it breaks it down into its principal components. We can use the summary function on this object, just like we can with most other models. In this example, the first two components explain the most variance in the model. We can see that 96% of the variance is explained with these first two principal components. Let's look at the attributes. Now there are many attributes of interest. The sdiv, rotation matrix, which are the variable loadings, center, which is the mean of each variable, and the scale, which is also the variance of each variable. How is this useful? PCA takes a dataset and converts it into a set of linearly uncorrelated variables called components. These components describe the variance within the dataset. Many of the variables may be correlated, and we can use PCA to describe how these correlations break down. We can explore these relationships a little further by using the biplot function. In this plot, each axis is one of the biggest principal components. Points that are close together have similar scores. In this example, you see points stacked in sort of a column, and all these values relate to the species Setosa. Now the red vectors that you see pointing, and there are 4 of them, one for each numerical variable of our dataset, those that point in the same direction have similar profiles. And in this case, petal length and width are closely related, which we can see by looking at the correlation table. And here you can see the high correlation between petal width and petal length, 0.96. Now, if a lot of this is unfamiliar to you, that's okay. I'm sure there's some people out there that have come across this and will like to know how to use this model with their datasets. I gave a brief introduction of principal component analysis and a few of the functions that are essential to it.